So we want to today give a general overview. We're going to talk about somatic and autonomic information. As we finished class last time, I gave you just some real basic anatomy things about the somatic and autonomic nervous system. So so far you have this general idea that there are neuronal cell bodies in the central nervous system. Their axons leave the central nervous system. In fact, from our histology presentation, you say central nervous system, you think brain and spinal cord. You see neuronal cell body. Neuronal cell body is carrying information to a skeletal muscle. That's a motor signal to a skeletal muscle. Where is that neuronal cell body? Well, we saw them. That's one of the reasons I showed them to you. Those beautiful motor neurons in the ventral horn of the spinal cord, the lower motor neurons. So these neurons we've seen already. They have myelinated projections by way of spinal nerves, and we're going to say some more about that today, projecting to the skeletal muscle using acetylcholine. In the autonomic nervous system, we have sympathetic and parasympathetic divisions, fight and flight, rest and digest. And we said we discuss the motor outputs of the autonomic nervous system using the language of ganglia. So we say the preganglionic projections of the sympathetic nervous system are in general short. They're myelinated. The postganglionic projections of the sympathetic nervous system, we say in general, are long. The dotted line here means to teach you they are not myelinated. This is unusual, and we'll point that out as I'm going to show you a picture of sympathetics here in just a sec. And acetylcholine on the presynaptic or preganglionic side, norepinephrine on the postganglionic side. The parasympathetic, the general rule is preganglionic projections are long because the vagus is the model here. So I'm going to show you that. Postganglionic projections of the parasympathetic nervous system are, in general, short because the ganglia of the parasympathetic nervous system are, generally speaking, located at the target. They're at the heart. They're at the intestine. They're at the stomach. These ganglia of the sympathetics are in a chain alongside the spinal cord. So I'm going to show you those. Now, the exception I finished class with was this one. I didn't talk any more detail about it. It's a very important exception, and that is the projection to the adrenal gland. Developmentally, during the development of these structures, the cells of the adrenal medulla are located in the same tissue that the neuronal ganglion cells of the sympathetic nervous system are located in. Which means that the cells of the adrenal medulla think they are postganglionic sympathetic chain ganglia neurons. In fact, they make norepinephrine just like these neurons do. So these are related. The adrenal medulla cells, they are known as the chromaffin cells. We will say much about this connection in this class. And in next semester, it gets even bigger. The adrenal medulla cells here, the chromaffin cells, produce norepinephrine and epinephrine. This is why we call our fight or flight response the adrenaline surge. That's what this chemical is. Epinephrine is adrenaline. It's produced by the adrenal medulla. These cells think they are ganglionic neurons of the sympathetic nervous system. They're related. They are, in fact, first cousins. They come from the same parent cells in the neurocrest ectoderm. They believe they are neurons. They're not. They're hormone-producing cells, but they think they're neurons. Now, the reason this is so important to point out here is because a sympathetic response has two major features to it. It has a short term and it has a long term. This connection, the neuronal connection, is a very fast signal, getting to structures very quickly. This signal, as you can see, has to make its way through the circulatory system. This one is fast and short-acting, and this one is slow and long-acting. So an adrenaline response, a sympathetic response, has both features, and this picture explains the neuroanatomical connections that describe that. All right, somatic, sympathetic, parasympathetic. Now, I want to give you a little bit more anatomy on these two. These are things, right, that will come up everywhere we go. We're not going to talk a lot about them while we're doing the muscles, but it's going to be difficult not to mention them in places. So we do it right here at the beginning. This is the general outline anatomy of the parasympathetic division. So there's some things you need to pick up now and then never forget them. So first thing you can see here is that the pre-ganglionic neuronal cell bodies originate in two places, in the brain and in the spinal cord. So most anatomy texts will refer to this division as the craniosacral division of the autonomic nervous system, craniosacral. The preganglionic neurons of the parasympathetic division that come off the brain are associated with 4 pairs of the 12 cranial nerves. They are cranial nerve 3, 7, 9, and 10. You'll have to learn their names today. I'm going to teach them to you. I'm going to do it now, and then I'm going to teach you all 12 names in just a moment. Oculomotor, facial, glossopharyngeal, vagus. 3, 7, 9, and 10. So we'll talk about each. I'll show them to you again in just a moment. Get their names. Learn their names. Learn the 12 pairs of cranial nerves. Learn them today. On old Olympus towering top, a fat vicious goat vandalized a hat. An acronym to help you remember their names. I'm going to give them to you in just a moment. 4 pairs of the 12 carry parasympathetic motor information. Now, this is a good time to point this out, because as we start the head, you got a test next week, and then I'm going to start the head right after that. As we start that, we start looking at these cranial nerves and where they go. One of the things we're going to talk about is the distribution of cranial nerve 3. This nerve is called the oculomotor nerve. The oculo. If I say ocular, where does your brain go? To your eyes, yeah? Ocular goes to your eyes, okay? So I'm going to show you the attachments of the 6 extrinsic eye muscles, the eye muscles that move your eyes around in your head. You're going to learn their names and their attachments. And what you're going to learn is that 4 of the 6 are controlled by this nerve. Now that is somatic motor information. That is this kind of information right here. This is information in a nerve, a cranial nerve, that goes to muscles, 4 of them in your eyes. The nerve passing through the superior orbital fissure between the greater and lesser wings of the sphenoid. You see why it was important for you to learn the bones? That's where we're going to find that nerve, okay? So cranial nerve 3, it says here, is part of the parasympathetic nervous system. It is delivering parasympathetic information to the eyes. Now, I can move my eyes consciously. That's somatic. What functional piece of my eyes is autonomic? What's that? Okay. That is considered, most of that information is considered somatic as well. So the levator palpebrae superioris that moves the eyelids, and the orbicularis oculi, those are considered. So you think you're not thinking about it, but really technically we say that's a somatic delivery of information to your eyes to make them blink. What else would your eyes do? Yeah, so when light goes into your eyes, the size of the hole that the light's going through changes, and you don't have control of that. That is a autonomic response. The parasympathetic nervous system goes to your iris. So I'm going to show you, as we work through the head, we're going to bring this up again, And what I'm teaching you here today is you learn somatic and autonomic, and you think, well, we'll just keep those separate. But you see what we're going to have to do? We're not going to be able to separate these, right? Because cranial nerve 3 carries somatic information to the eyes, and it carries autonomic information to the eyes. So motor pathways illustrated in these nerves for both. And so cranial nerve 7, which is the facial nerve, is also one of these nerves that does that. It carries both parasympathetic motor and somatic motor. Cranial nerve 7 is the facial nerve. That's the muscle, that's the nerve that controls all the facial expression muscles in your face. So yes, somatic, yes, autonomic. Okay, so learn the ones here for parasympathetics, 3, 7, 9, and 10, the cranial division. Down here at the bottom, you see the sacral division fibers. So there's a very important place, where the influence of the cranial division and the influence of the sacral division are seen handing off to one another. And so this picture right here actually gives you an idea about where that happens. I'll make a little bit bigger deal about it when we get to the blood vessels. But you can see that most of the stuff that we think about for autonomics, heart, lung, glands, digestion, hormones, digestion, most of this stuff in the thoracic and abdominal body cavity that we think about as being autonomic. You know, we don't think, come on, heart beat. We don't think, come on, lungs, breathe. We do these things. The airways are controlled autonomically. The secretions of the enzymes of the liver and the bile and the gallbladder, we know that's all autonomic. Okay? The reason I point all that out is because that information fits the model. The model I taught you was this one. I said, generally speaking, preganglionic parasympathetics are long, postganglionic parasympathetics are short. The ganglia are at the targets. So that model is actually modeled after this one, cranial nerve 10. So look at what cranial nerve 10 has the capacity to influence. If you have some kind of vagal response in the body, something you've done to the vagus, you're going to impact most things in the thoracic and abdominal body cavity. A vagal response is very dangerous. So this nerve in your neck is found in a sheath with the carotid artery and the jugular vein, the internal. And so if someone wants to go in and get access to the carotid, you cannot touch the vagus, because touching a nerve stimulates it. And if you touch the vagus during the surgical procedure, you will cause the heart to, you could, if you touched it, cause the heart to slow down and even stop. And you could make the digestive system over-respond, and you could have a massive digestive system overload. So very important, cranial nerve 7 as the model of the cranial division of the parasympathetic nervous system. 3, 7, 9, and 10, cranial division, vagus is the model. Now when you get down here to the gut, you can see there's a handoff here, and you can see the sacral divisions are handling some of the digestive system, and they're handling things in the pelvic body cavity, things inferior to the parietal peritoneum in the pelvic body cavity. So you can see reproductive structures indicated here from the sacral divisions. That trade-off happens in the large intestine. So we'll make a point of that, because that's also where the blood vessels trade off. The superior mesenteric gives way to the inferior, vagus gives way to S1 sacral. So there's a trade-off that happens in the digestive system. But this is the general anatomy, general features of parasympathetic outflow, the craniosacral division. Second one, sympathetic. The sympathetic division is oftentimes referred to anatomically as the thoracolumbar division. The preganglionic cell bodies of the sympathetic nervous system arise in the spinal cord between T1 and L2. Between T1 and L2. Cell bodies of the sympathetic motor output arise in the thoracolumbar divisions of the spinal cord. Generally speaking, their preganglionic projections are myelinated and short because there is a chain of ganglia along either side of the spinal cord. It's bilateral, it's on both sides, that receive information from the preganglionic inputs coming out of the spinal cord, from T1 to L2. Short preganglionic projections. These are myelinated. You see their name? Why are they called white?
Because it's white matter.
It's white matter. Okay, so what would I call the ones on the other side?
Gray.
Gray. Yeah, so if these are white rami communicantes, what will be the ones on the other side?
Gray.
Gray rami communicantes. Yeah. So this is preganglionic sympathetic short to the ganglion. This is the model. Now, there are places where that model is, there are exceptions to this model. We say, when we define these things, we say long, short for parasympathetic. We say short, long for sympathetic. But there are exceptions. And you can see them here. Can you see how the white rami here continue through the ganglia here in several of the divisions without synapsing? You guys see that? So the best model for sympathetics for short-long is really in the upper divisions of the thoracic cord. You can see these dotted lines coming up here supplying thoracic structures and structures of the head and neck. So this really serves as our model when we teach sympathetics, because a lot of the stuff in the gut is controlled by ganglia that are not in the chain. So in this case, the projection comes off the spinal cord, passes through the ganglia, and doesn't stop. The axon just keeps on going. And after it passes through, it becomes a set of nerves, and this goes from top to bottom. These nerves are generally referred to as splanchnic nerves, and they're cardiopulmonary splanchnic nerves as well. Splanchnic nerve, that's a very common term there for the sympathetic nerves that innervate structures from the head all the way through the abdomen. All right, so that's not important yet. But I do want you to see the general features here. As these guys pass through, they're going to form synapses in ganglia that are not in the chain. So what I'm telling you is there are clusters of cell bodies for the sympathetic nervous system that are closer to the organs than the chain is. Remember, in the parasympathetic nervous system, the model is the ganglia are located at the target. So you have a long projection out to the ganglia, and when you get to where you're going, you make a synapse. The general rule for sympathetics is you come off the spinal cord, go a short distance, and make a synapse. But there are exceptions to that. And you can see these major exceptions come here as you move down through thoracic toward the lumbar divisions. You see these major exceptions of these nerves passing through the ganglia without synapsing, making their first synapse in what are called peripheral ganglia. And so there are a bunch of them, but the three big ones are associated with blood vessel names that you will have to know lots of detail about. And these blood vessels are the celiac artery, so there's a celiac ganglion, the superior mesenteric artery, so there's a superior mesenteric ganglion, and the inferior mesenteric artery, and there's the inferior mesenteric ganglia. So as we work our way down the abdominal aorta much later in this class, these will be the three major vessels that we will have to learn the branches of to supply the gut. The celiac, the superior mesenteric, and the inferior mesenteric. The three big blood vessels to supply things in the abdominal body cavity. And at those locations, there are sympathetic ganglia that seem to be relay stations to control the same structures that the blood vessels are supplying. So there are sympathetic ganglia located along the abdominal aorta at key locations. named for where these blood vessels are: celiac, superior and inferior mesenteric. All right, now, there's another exception on this picture that I pointed out to you on the opening slide. So if my definition works, projection from the thoracic division of the spinal cord out to the chain ganglia, making a synapse, short, acetylcholine. Then the projection from here, unmyelinated, passes out to the target, long, norepinephrine. That's my rule. That's my anatomy rule. The first exception the exception that I've just pointed out to you here is, in a lot of cases, you don't synapse in the chain. You go right through. You don't go all the way to the organ, but you get closer to it, and you synapse in a ganglia associated with the three big blood vessels: celiac, superior, and inferior mesenteric. Then, you see the dotted lines? The postganglionics are unmyelinated, and they go out to the various structures. So it still works. It's shorter. The ganglia are not at the targets. They're closer, but they're not there. There is one exception to this rule that doesn't fit any of the others. And it can be seen in this picture as the continuation of the solid green line. So, which gland does it go to? And did you expect to see that? It goes to the adrenal gland. Specifically, it goes to the adrenal medulla, the cells of which think that they are sympathetic chain ganglion cells. So you can see the solid green line here passing through without making a synapse and making its first synapse here at the adrenal gland. So what is the sympathetic neurotransmitter? What is the sympathetic chemical being released at the adrenal gland? No. This is a preganglionic projection, right? That is a long preganglionic sympathetic projection. What is it? Acetylcholine, yeah. So this is a major exception here, and we point it out again on this picture. Now, students sometimes ask, I want to show it to you, they say, okay, well, you said these cell bodies are located in the lower motor neuron. These are the lower motor neurons in the ventral horn of the spinal cord. And I showed you a picture of that in the histology section. Students want to know, well, where are these? Okay, so you'll have to be patient with me. We'll get to those. But one of them I want to show you now because it helps me introduce the spinal cord. So this is a transverse section of spinal cord, and there's some things on here you know already. For example, you know what kind of cell bodies are here. This structure right here is labeled the spinal ganglion. Do we have another name for this already? You know, if you pick up something and the annulus is weakened between L4 and L5, and the pulp proceeds out to press on the ganglion into the transverse process, creating enormous amounts of back pain. Remember that? These are your dorsal or posterior root ganglia. And I used it to define ganglia for you. I said, this is where all the cell bodies are. A cluster of unipolar cell bodies here in this ganglion. What kind of cell bodies? Sensory or motor?
Sensory.
Sensory, yeah. Are there any exceptions to that? No. No exceptions to that. Everything sensory goes this way, dorsal side. What kind of information is on this ventral root then? This is all sensory, then this has to be all motor. And when we get out here to the nerve, does the nerve have sensory in it?
Yes.
Does it have motor in it?
Yes.
Does it have somatic in it?
No.
See, it does. Somatic does what? Go to the muscle, right? Somatic to muscle. Does it have autonomic in it? Okay, so Put the anatomy pictures together in your head, young people. This is the reason for it. If I took a section right here, I took a little section of this piece. It's gray. What would I expect to find there? This is the ventral horn of the spinal cord. What will I find right there? Mostly myelinated axons or mostly unmyelinated cell bodies? Mostly unmyelinated cell bodies, right. And what is their purpose?